All right, let's talk about a question that trips up so many people in coding interviews. You're there, you're in the zone, and then they hit you with it. So, for this problem, would you use iteration or recursion? And your mind just goes blank. We've all been there. So, today, we're going to break this whole thing down so you can absolutely ace it next time.
Just think about that for a second. You could have two pieces of code. They do the exact same job, finish in the exact same amount of time, but one of them is a total memory hog, while the other one is super lean and efficient. That right there, that's the real tension between iteration and recursion. And getting that difference, that's what separates an okay answer from a truly great one.
So we've got these two different paths to get to the same destination. To really understand the trade-offs, the stuff your interviewer actually cares about, let's start with a really simple analogy for each one.
First up, we've got iteration. This is probably the first way you learn to do things, using for loops, while loops to just repeat a task over and over. Think of it like you're climbing a staircase. You start at the bottom and you take one step, then the next step, then the next. You've got one little marker with you and you just move it up each time. You always know exactly what step you're on and you only have that one thing to keep track of. It's direct, it's simple.
Now, recursion. This is where things get a little more magical, a little more mind-bending. A recursive function solves a big problem by just calling itself on a slightly smaller version of that same problem. So with our staircase, the logic is kind of like, hey, to climb all 10 steps, all I really need to do is climb 9 steps and then take one more. So it delegates that task and that task delegates and so on. But here's the really important part. Every time it delegates, it leaves behind a little bookmark to remember where it was. And those bookmarks, well, they're going to become very important in a minute.
Okay, so theory and analogies are great, but let's get real. It's in the actual code where these trade-offs really come to life. So let's compare these two approaches side by side with 3 classic computer science problems and see how they stack up. We're going to start with a classic, one you've probably seen 100 times, calculating a factorial. It's super simple, super clear, and it highlights the number one trade-off we're talking about perfectly. Okay, so on the left, you've got your standard iterative approach. A good old for loop, a variable that keeps track of the result. Pretty straightforward. On the right, that's the recursive version. It feels a lot more like a math definition, right? You have a base case, that's the emergency brake that stops the function from calling itself forever, and then you have the recursive step, where it calls itself with n-1. It looks elegant, for sure, but that elegance comes with a hidden cost. And here it is. This is the punchline. Look at the time complexity. That's how long it takes. Both are O of n. They basically do the same amount of work. No surprise there. But now, look at the space complexity. The iterative version is O of 1. That's constant space. It doesn't need any more memory, whether you're calculating the factorial of 5 or 5,000. But the recursive one, O of n. Its memory usage grows right along with the input. And why? It's because of all those bookmarks we left on the staircase. Each one takes up a little bit of space. So, okay. Recursion costs a little memory for factorials. Big deal, right? Well, let's move on to our next example, the Fibonacci sequence. Because here, choosing the wrong approach isn't just a little inefficient. It can be an absolute performance nightmare.
Whoa, yeah, look at this chart. The iterative approach is that tiny little bar on the left. It runs in linear time, O of n. It just chugs along nicely. But the naive recursive one, the one that just blindly calls itself twice, it runs in exponential time. That massive bar on the right shows you how quickly this spirals out of control. It's because it's recalculating the same values over and over and over again. This is a classic interview trap. All right, for our last case study, let's look at binary search. This is like the poster child for divide and conquer algorithms, where you solve a problem by constantly cutting it in half. It's a place where both approaches can feel pretty natural.
And what do we see? It's the exact same pattern. The time complexity is wicked fast for both, O of log n. That's the power of divide and conquer right there. But the space complexity tells that same familiar story. Iteration, flat, constant, O of 1 space. Recursion, its memory needs grow, this time logarithmically, right along with the input size. Again, it's all about those bookmarks.
So we've seen 3 times now that recursion uses more memory, but we haven't really talked about why. To get that, we need to pull back the curtain on the computer itself and look at a really fundamental concept called the call stack. This is where all those bookmarks actually live.
So let's just ask the question straight up. When a function calls another function,
how does the computer remember where to go back to when it's done? The answer is the call stack. And when a function is calling itself, this has some pretty huge implications. Okay, so let's just walk from this. When we call factorial of 3, a little task, or a frame, gets pushed onto the stack. That task then calls factorial of 2, which pushes another frame right on top of it. This keeps going until we finally hit our base case, factorial of 1. At this point, the stack is as tall as it's going to get. Then, as each function finishes and returns its value, its frame gets popped off the stack, one by one, until we're all the way back at the beginning. This whole stack of frames, our pile of bookmarks, that's the ON space cost we've been seeing. Now that you get the call stack, there is a critical language-specific detail that you absolutely have to know, especially if you're a Python developer. This is a real pro-level tip, so listen up. And here's the kicker. Some programming languages have this really clever trick called tail call optimization. Basically, if the very last thing a function does is call itself, the language is smart enough to just reuse the current spot on the call stack instead of adding a new one. It makes recursion just as memory efficient as iteration. But here's the catch. Python does not do this. So in Python, every single recursive call adds a new frame to the stack, no matter what. And if you go too deep, you'll literally crash your program with a recursion error.
Okay, so we've got all this knowledge about stacks and complexity and bookmarks. How do you actually use this to sound brilliant in an interview? Let's boil it all down into a simple, actionable playbook that's going to impress anyone.
Here is your strategy. You use recursion when the problem itself is just naturally recursive. Think about walking through a family tree or a file system. The code is often way cleaner and easier to follow. But you choose iteration when memory is super critical, or if you're in a language like Python where you can have a really deep recursion. Now here's the pro move for the interview. You write this simple, elegant recursive solution first. Then you turn to the interviewer and say, this is clean, but I'm aware it uses O of n stack space. To optimize for memory, I can rewrite this as an iterative solution. That shows mastery. Just always remember the golden rule. The time it takes is usually the same. The real battle is fought over space. So there you have it. You know the what. Iteration is loops. Recursion is a function calling itself. But the real mastery, the thing that will make you stand out in an interview, is explaining the why. It's about understanding that recursion's elegance comes at a price, and that price is memory. It's paid for by building up that call stack, that pile of bookmarks. When you can articulate that trade-off clearly, you're not just writing code, you're engineering a solution.